Alright class, let's look at Learning Objective 2-1. Explain the meaning of the slope of position over time graphs. So we got this camera, we got this tortoise here. Let's have this tortoise move and let's look at the tortoise's motion. We want to measure position. So think about a camera taking photos of the object every second. Position is the distance away from the origin. Position is the distance, so just follow along, distance away from the origin. And the origin is the starting point. So if my tortoise starts here at 1 second, 0 Mississippi, 1 Mississippi. At 1 Mississippi, at 1 second, this tortoise has gone this distance. Distance away from the origin. Now, changing position. Objects that are moving faster will have a larger change in their position for each second. Objects that are moving faster will have a larger change in position for each second. So let's take a peek at this hare here, the tortoise and the hare, right? So 0 Mississippi, 1 Mississippi, 2 Mississippi. At 1 Mississippi, 0 Mississippi, 1 Mississippi, this hare, rabbit, has gone this distance. Quite a bit farther than our tortoise up here. Let's just take a peek at those. Let's compare. Oh yeah, definitely. We have a larger change in position for each second for this faster creature, this hare. Finding velocity. Velocity is the distance traveled per unit of time. Velocity is the distance traveled per unit of time. Unit of time. Distance per second. It's written mathematically as the change in position over the change in time. So I'm going to zoom in quite a bit here. The change in position divided by the change in time. And in physics, that x means its position or its horizontal position. You could write this. This is the same as saying something like the change in position, you can say distance, over the change in time. Yet another, the same way to, actually we'll keep it there. We'll keep it there. I like this version the best, so I'm going to erase this. Change in position over the change in time. On these diagrams, these little tortoise diagrams with the camera, this is the gap between the dots. So that length between the dots there. We measure that in meters. Next page. So another way to write that would be, the best way is simply this symbol right here. V. V is velocity. Boom. Change in position traveled per unit of time. Okay. Objects with a higher velocity will cover more distance each second and show a larger gap between the dots. Objects with a higher velocity will cover more distance each second and show a larger gap between the dots, according to our model up there, our diagram. Now, let's think about something a little more complicated, but it's not so bad. Negative velocity. Velocity is a vector, a unit of measurement that requires direction. Velocity is a vector, a unit of measurement, that should say measurement, that requires direction. So if you have a velocity, that means you have an amount of your velocity or a magnitude, and it also means that you have a direction. Let's look at this frog. This frog, I'm going to write v for velocity, and its velocity is this direction, going to the left. Vectors are represented as arrows. Vectors are represented as arrows. Objects that move toward the origin, that move towards the origin will be losing position, and therefore they will have a negative velocity. A negative velocity. This guy's losing position. I don't know if losing is the right word. He's still moving, but he's moving toward the origin. All that means, positive and negative for velocity, it just means, are they moving to the left or to the right? Are they moving up or are they moving down? The sign, I'm going to write this down. I think this is an important idea. The sign, meaning positive or negative, of the velocity tells you the direction. Tells you the direction, or the direction the object is moving in. So let's see here. We've got a position versus time graph, and when we look at it, at 1 second, we see it's traveled this initial distance, d, and you can see that if we go over and look at that model over there on the left. At 2 seconds, he's traveled twice the distance. Twice the distance. And you can see that right there. That's twice the distance. At 3 seconds, he's traveled 3 times the distance. D, D, D. He's traveled 3 times the distance. So if you're thinking ahead here, you're almost thinking, this looks like we're looking at slope here. We can see that this guy's got a constant slope, so we know that we're traveling at a constant velocity. This is a constant slope. And we also can see from this graph that the slope is positive. The slope is positive, which means he's moving in the positive direction. We often in physics will say that the positive direction is to the right and the negative direction is to the left. So we can confidently say that this tortoise is moving to the right because the slope is positive and he's also moving at a constant velocity. The velocity is not changing. Now, looking at another graph, let's scroll down a little bit more. Same deal here. We've got this hare. Now, at 1 second, you can see that this hare has traveled this distance, d. At 2 seconds, this hare has traveled this distance right here, this much greater distance. So you can see that, oh my gosh, which slope is steeper? Well, we'll look at that in a second. And you can see that this frog has been moving towards the origin. So at 1 second, this frog has moved this distance, in the negative direction. At 2 seconds, this frog has moved all the way down to the origin. He's at the 0 position mark. He's at the origin there. Position graphs. Graphing the position of the object each second. The y-intercept gives the position at 0 seconds. So if we look at this frog here, he's 2 distances away at the y-intercept, right here at the origin. So he starts kind of far away from the origin spot. The slope of a position graph. Slope is the change in y over change in x. On these graphs, you can write that mathematically as the change in distance or position divided by the change in time. Therefore, the slope of a position graph is the velocity. Therefore, the slope of a position graph is the velocity. Righto? So if we look at these three different lines, we can kind of guess or match which slope matches which velocity and which velocity matches which creature here. So if we look at which slope is the steepest, this slope right here is the steepest. It's got the highest rise over run, and that's got to belong to Mr. Rabbit here, or the hare. And if we look at a slope that's less steep, this guy is a less steep slope, so this must be our tortoise here. So the less steep the slope is, the smaller the slope is, and the smaller the velocity is, because the slope of a position versus time graph is the velocity. The slope of a position versus time graph is the velocity. I just memorized that statement. That'll just help. All right, so if we look at this negative slope here, that slope belongs to none other than Mr. Frog here, because he is moving to the left, or in the negative direction. So for complex position graphs, always look at the slope and think of the velocity. Always look at the slope and think of the velocity. So let's think about it. For this first section, we'll call this section A. We know that this guy, whatever's moving, is moving in the positive direction. He's got a constant velocity. Whoop. And he's probably moving pretty fast because the slope is pretty steep. Now, I think that when the person was drawing this graph, they were trying to make this red line just completely flat. So let's imagine that it's flat. And if it's a flat slope, that means that the slope of, we'll call this section B, this means that the slope equals 0. Because if there's no rise, if rise divided by run, rise is 0 divided by anything is going to be 0. So that means that at B, there's no velocity. There's no velocity. And you can see here, rise over run, this is going to be its velocity, the rise over the run. And this, again, here we have no velocity. Right here, the rise divided by the run. The rise is the change in position over the change in time, which is its velocity, so it's got some velocity there. And right here, at the very top, he's got no velocity because there's no slope. And right here, this last section, the slope is negative. The slope is negative and constant. So we know that he's got a velocity that's going, I don't know, to the left in the negative direction, and it's constant, so it's not changing. We can see right here that the slope is the same there, is the same there, is the same there. That slope is not changing. A lot of students make mistakes to go, oh, right here, look, check this out. This is a decreasing slope. No, that's not a decreasing slope. We just know that it's a negative slope, and we know that that slope is constant. All right, cool. Hopefully we learned a lot. That was a long video.